Hello, welcome to this video 8-1, and today we're going to talk about graphing exponential functions with base 2 exponential functions and base 10. So we're going to go ahead and dive in, and I'm going to tap into your prior knowledge, and that is looking at these two functions here. First, identify which function is exponential growth and which one is exponential decay, as well as determine the equation of the horizontal asymptote. Well, in your prior studies in Math 1, you would have determined that if a function is decreasing exponentially, that this is exponential decay. And if a function is growing, getting bigger and bigger and bigger, that's going to be exponential growth. Now, exponential functions also have horizontal asymptotes, and that's where our function will approach at one end and get really, really close to. So for our first example here, the exponential decay function, our horizontal asymptote is y equals 0. Our function is decaying and getting smaller and smaller and smaller towards y equals 0. It'll never actually fully be 0, but it's going to get really, really close to it. As far as our second example here, our second function, f of x equals 2 to the power of x minus 3, this is exponential growth, and our horizontal asymptote here is y is equal to negative 3. That's this horizontal asymptote down here, and our function, as x approaches negative infinity, is getting closer and closer and closer to that value, but it will never ever approach it. Okay, so let's go ahead and look at some exponential functions and define them. An exponential is a function of the form, and there's a lot here, f of x equals a times b to the power of c times x minus h plus k, where b is greater than 0 and b is not equal to 1. Plain and simple, again, you'll see here the parameters that you're familiar with. We have an a value, an h value, and a k value. Now we also have a new parameter here, c. That is your horizontal factor, your horizontal stretch or compression, as well as reflection. Now b here, this is the base. This is the base of our function. That's always going to be a constant value bigger than 0. It has to be positive. It cannot be negative, and it cannot be equal to 1. Okay, so the domain of every exponential function is all real numbers. I can plug in anything into these functions because an exponent can be any real number. There's no limitations on what x values can be. There is also no single parent exponential function because each choice of the base b determines a different function. And we're only going to look at today f of x equals 2 to the x and f of x equals 10 to the power of x. Okay, so these are our parent functions for today. So we're going to go ahead and graph, that's our goal, and then also identify some key features of these functions. But what do we want to include? Well, we want to go ahead and include the horizontal asymptote. Now the horizontal asymptote is y equals k. Whatever your k value is, you want to include that. And then we're going to include the key points, which I'll show you here in a moment, including the y-intercept and 0, if reasonable for the 0. And then also our end behavior. So let's go ahead and look at the parent function for the function f of x equals 2 to the power of x. Okay, this is the parent function for all functions with a base of 2. So note, here is the general form, and you'll see this with different parameters here. Okay, and here is a graph of 2 to the power of x. Now what I want you to pick up from this lesson is that exponential functions, they all have a y-intercept of 0, 1. That is the parent functions with no stretches or compressions or shifts. Okay, and then their second point is whatever their base is. So 1, 2. In this case our base is 2. So if I go ahead and if I have my function f of x equals 2 to the power of x, if I evaluate at 1, I get 2 to the first, which is 2. Okay, so those two points are important points to remember just in the general approach to exponential functions. Now, key points that we're going to go ahead and include in our graph are going to be these following points. -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. And you'll notice that these points, they grow by multipliers of 2. And that should make sense if you have an exponential function, right? Every x value that you increase, you're multiplying by 2 one more time. So these will increase by a factor of 2. Now, some of the key features of rational functions, again, as previously mentioned, the domain is negative infinity to positive infinity. Your range is going to depend upon where your horizontal asymptote is, and also if you have reflection or not. In this case, our range is 0 to infinity. 0 is the lower bound of this function. And that's because our horizontal asymptote is there at 0. Again, if we have a translation down or up, that's going to change that. And then lastly, end behavior. Our end behavior for exponential growth functions, and that's what we're looking at today. As x approaches negative infinity, our function's going to approach the horizontal asymptote, and in this case, it is 0. As x increases unbounded in the positive direction, our function's going to grow extremely rapidly. So as x gets bigger and bigger and bigger, our y values are going to increase unbounded towards positive infinity. Okay, let's go ahead and look at our first example here. Graph the function and state the key features. G of x equals 2 to the power of x minus 2 plus 1. If we're going to go ahead and graph this, it's important to know what your parameters are. So our a value is 1, our h value is 2, and our k value is a positive 1. Okay, these are important because they're going to shift our graph around. Number 2, you need to go ahead and figure out what your horizontal asymptote is. This is going to be a key feature of your graph. And remember, it's just y equals k. Whatever y, I'll put this in parentheses, so I would write this down, y equals k, whatever that is. So you can go ahead and add that here to your key features, y equals 1. There's our horizontal asymptote. Okay, so I'm going to go ahead and I'm going to place some axes here. We have our x-axis, and we have our y-axis. Okay, and I'm going to go ahead and plot my horizontal asymptote at 1. So a dashed line for your horizontal asymptote. There's y is equal to 1. And then I'm going to go ahead and step 3, I'm going to find what I like to call the pseudo origin. Where do I want to frame my function, my pseudo origin? And that's going to be h, comma, k. Whatever your h, comma, k is. And what I'm doing is I'm building in my translations, my horizontal and vertical shift. So 2, comma, 1. So I'm going right 2 and I'm going up 1. This is like my new pseudo 0, 0 point here. I'm going to graph all my points from this point, okay? And that builds in our translations. So step 4, I need to plot the rest of my key points, okay? Now you're going to get these from your table, or you can generate them just by knowing what the function is. So I'm going to plug in -1. That'll give us 1/2. 0, 1, 1, 2, 2, 4, and if room permits, I'll have 3, 8. So from this point, from my pseudo origin right here, I'm going to go ahead and I'm just going to graph these. So I'm going to go left 1, up 1/2. I'm going to go back to my pseudo origin, and I'm going to go 0, 1. Okay, I'm going to go right 1, up 2. Back to my pseudo origin. I'm going to go right 2, 1, 2, and then up 4, 1, 2, 3, 4. And I don't think I have room, but if I went right 1, 2, 3, I would go up 8. 1, 2, 3, 4, 5, 6, 7. I'm off by 1, but my point would be there. Okay, and so my graph, I'm going to go from my horizontal asymptote all the way through these points here. and there is my function. Okay, notice it looks just like an exponential function should. My points from 1 to the next are growing at a rate of 2. So up 1, up 2, up 4, up 8. And my shift is up 1. And I'm centered right here, right 2. Okay. So there's my graph. We'll go ahead and do another example, but I want to talk about the key features. As said, our function goes from negative infinity to positive infinity. So negative infinity is less than x, which is less than infinity. And as an interval, that is negative infinity to positive infinity. Our range is going to be all of the y values where y is bigger than 1. Notice that's our horizontal asymptote, and my function is growing. It's getting bigger and bigger and bigger from 1. As an interval, that's going to be 1 to infinity. Now my y-intercept, that's going to be right here. I don't want to approximate this. This I want to be extremely accurate with, but notice that there, for the y-intercept, my x value is 0. So in order to determine what that y-intercept is, I'm just going to go ahead and evaluate my function g of 0. I'm going to plug in 0. So I get 2 to the power of 0 minus 2 plus 1. This gives us 2 to the negative second, which is 1 over 2 squared plus 1. And so we get 1/4 plus 1, which is going to be 1.25. So 0, 1.25. That is our intercept there. And then I'm going to go ahead and graph or just state my end behavior. So as x approaches negative infinity, this is the left, my function g of x is approaching 1. That horizontal asymptote here, values will get really close to 1. And then as my x values increase towards positive infinity, my function g of x is going to get big in the positive direction. So g of x will approach positive infinity. All right, here is example number 2. They say graph the function and state the key features. G of x is equal to negative 2 x to the power of x plus 3. In this example, our step 1, again, is to find the a, h, and k. Our a value is negative 1. Again, our base is 2 with an h value of negative 3, and our k value is 0. With a k value of 0, this means that our horizontal asymptote will be y is equal to 0. Okay, and we can go ahead and place that in our key features. That's our horizontal asymptote. So with this graph, before I go ahead and place my x and y axis, I want to comment that we have an a value of negative 1. With an a value of negative 1, that's going to cause a reflection. So I'm going to go ahead and place my x-axis up more. I'm going to place it up here. And I don't have any translations up with my asymptote. So the x-axis is fine there. And I'll go ahead and place my asymptote right on top of it. And then my horizontal shift is left 3. So I'm going to go ahead and place my y-axis more down the middle. So let's go ahead and place it here, down the middle. Okay, here's our y-axis. All right, and again, step 3, I'm going to go ahead and place my, what I like to call my pseudo origin. This is where I graph all of my key points from, and again, that is h comma k, so negative 3 comma 0, which is right here. So I'm going to graph my key points from that location. And again, the key points that you want to plot for base 2 include negative 1, 1/2, 0, 1, 1, 2, 2, 4, and if possible, 3, 8. So let's go ahead from this location. I'm going to go ahead and go left 1, and instead of going up 1/2, again, we have reflection. So you can also do this. I have some students who like to multiply times the y value. times the a value, so multiply all of these by -1. However, this is very easy conceptually, that I'm just going to go ahead and reflect. Instead of going up, I'm going to go down. So down a half, down 1, right 1, down 2, right 2, down 4, and then right 3, down 8. Okay, and then there is our key points. So we'll go ahead and try to graph a smooth curve through these points. Okay, add arrows, and there is our graph. Ta-da! Okay, and just think about this. Does this kind of adhere to the reflections that we're used to seeing? I'm shifting left 3 units, right? So my key point, left 3, 1, 2, 3, and then we reflect. Yep. So I'll go ahead and write down the key features. Domain, these are the x values where negative infinity is less than x, which is less than infinity. And in plain old interval notation, that's just negative infinity to positive infinity. Now my range, notice I have a maximum. I have an upper bound now. I don't have a lower bound. We're just going to negative infinity. So this is the y values, where y is less than 0. And an interval notation, that's going to be negative infinity to 0. Our y-intercept, this time I don't have to evaluate g of 0, although if you did want to evaluate your y-intercept, you could go ahead and compute that. However, this one is given on the graph to us. It's one of our key points, 0, -8. And then lastly, our end behavior. For the left side, as x goes to negative infinity, our function g of x is going to 0. And as x goes to positive infinity, g of x is going to negative infinity, increasing unbounded. Okay, so there's our second example of graphing exponential base 2. I do have a practice problem here for you. Please go ahead. I'd like you to pause the video, and I'm going to show you the solutions here in a moment. All right. Hopefully you pause the video. Here is what your graph should look like. You have an a value of 1. H is a positive 1, so you're shifting to the right one. And your k value is -2. So we have a horizontal asymptote of -2. And our pseudo-origin is just going to be 1 to the right. So looking at the key points, left 1 up a half, up 1, right 1 up 2, right 2 up 4, and then right 3 up 8 gives us those key points. Domain, negative infinity to positive infinity, and our range is -2 to positive infinity. The y-intercept, that is one of the key points, so you could have it there, or you could calculate it by evaluating g of 0. Our horizontal asymptote, y equals -2, and then our end behavior. As x goes to negative infinity, our function is approaching -2. And then as our x values increase towards positive infinity, our function is increasing unbounded in the positive infinity direction. Okay, so there is our practice problem. The next couple of slides are just going to reinforce this idea of how do we determine what the y-intercept is. Again, remember, you're going to evaluate a y-intercept by evaluating what the function is at x equals 0. Here are all of the points of a y-intercept, and they all have an x value that is 0. So if I go ahead and I plug in 0, here I have 3 times 2 to the power of 0 plus 4 minus 6. This is going to give us 3 times 2 to the 4th power, which is 16. And 3 times 16 gives us 48 minus 6, which gives us 42. So your intercept is going to be 0, 42. All right, here is a practice problem. Go ahead, please pause the video and try this example. All right, hopefully you tried that. You should have gotten 0, 4, and here's the work that you can go ahead and look at. All right, next question, multiple choice. What is the horizontal asymptote for this exponential function? Hopefully you said y is equal to 7. That is B. That is because our k value is 7. All right, how about this example? What is the horizontal asymptote for this function? Hopefully you said D, y is equal to 0. That is because our k value is 0. Okay, I have one more example for you, and this time I'm going to introduce the exponential function f of x equals 10 to the power of x. This is another exponential function, again, where our base is 10. And I want to point out the two key points that I talked about at the beginning of the video. The first one is our y-intercept for the parent function, 0, 1. Anything to the power of 0, regardless of what the base is, anything to the power of 0 is 1. Additionally, if I go ahead and evaluate at 1, I get 1, whatever that base is. So 1, 10. Our key points for this exponential function, base 10, notice how it grows really, really fast, are these 3 points. Negative 1.1 or 1/10, 0, 1, and 1, 10. This grows super fast and decays really fast, so I don't have significant points too far out, right? So we're going to stay pretty centralized here. Notice the key features, very similar to our last exponential function. Domain, range, exactly the same. Horizontal asymptote at 0, and end behavior is exactly the same. So let's go ahead and look at this example. G of x is equal to 10 to the power of x plus 1 minus 6. So again, step 1, identify your a, h, and k. A is 1, h is negative 1, and k is equal to negative 6. What this tells me right off the bat is we have a horizontal asymptote at y is equal to negative 6. Okay, so we're shifting down 6. And then step 3, my pseudo origin that I'm going to go ahead and graph my points from are negative 1, negative 6. So I'm shifting left 6. So let me go ahead and place a set of axes here. Okay, here's my x-axis. I'm going to start, actually I don't want to start that low. I want to start up higher because I have to shift down 6. Shift down 6, so I'm going to start up here. Here's my x. And then my y value, I'm shifting left 1, so it doesn't matter too much. Okay, here's my y-axis. And then I'm going to go ahead and plot my origin. So we're down 6. Down 1, 2, 3, 4, 5, 6. Here is our horizontal asymptote. Okay, and then our pseudo origin is just shifted left 1. So kind of like right here. So I'm going to go ahead and graph my key points. Step 4, I guess, key points. So we have x and then 10 to the power of x. So I'm going to go negative 1. That's going to be 10 to the negative first, which is just 1/10, very small. Plug in 0, we get 1. 1 gives us 10, and we can't go much further than that. So we'll go ahead and plot these points. 1/10, if I go left 1 from our pseudo origin, up 1, and then up 10. So 6 plus 4. There we go. And then here's our graph. And notice this graph grows really fast. Really fast. And that second point is going to hit 100. So there it is. And then we can discuss the key features. Domain, exactly the same. X, such that negative infinity less than x less than infinity. And interval notation, negative infinity to positive infinity. Range, these are the y values where y is greater than negative 6. And an interval notation that's negative 6 to infinity. Our y-intercept, that was one of our key points on our graph, 0, 4. and then the horizontal asymptote y equals -6. Our end behavior, as x approaches -infinity, g of x is going to the horizontal asymptote, which is -6. And then as x goes to +infinity, g of x is increasing unbounded towards +infinity. Okay, so there is exponential function base 10. Not much of a difference, just your key points. That's it. That is it. Okay, so here is a practice problem. Please pause me, go ahead and try this example. And also, what's your a value? Note, what's your a value? What's that effect? Okay, so unpause me in a second. I'll show you the answers. All right, here are the solutions. Hopefully you got this looking function. We're shifted up 3. Y equals k is 3. And then we're shifted to the left 2. So our pseudo origin would be right here at -2, 3. And then our key points, left 1, down a tenth, because our a value is 1. So we have a reflection. And then I'm going to go down 1 instead of up 1. And then right 1, down 10, which takes us down to -7. Now, here's the domain and range. You can check those. Our y-intercept is not one of our key points. So you can go ahead and compute it this way, or think about what your next point on your graph would be. If I went one more right, I would be going down 100. So that would take you to -97, 0, -97. Here's our end behavior. As we go, x values increase in the negative direction unbounded. Our function approaches 3. And as x goes to +infinity, our function decreases unbounded towards -infinity. All right, that is it. I do have a closure question. Will an exponential function always have a y-intercept? Explain. Will we always have a y-intercept? And will it always have a 0? Go ahead and think about that, and I'll show you the response here in a second. All right, since our domain is -infinity to +infinity, an exponential function will always have a y-intercept. I can always plug in 0, so yes. However, a 0, not so much. If I'm shifted up, or if even the parent function, just think about that as an example, we're not guaranteed a 0 to cross the x-axis, depending upon where our function is. Okay? All right, hopefully in this video you learned how to graph exponential functions of base 2 and base 10 and learn something about the key features. Talk to you guys in the next video. See ya.